Hello again, YouTube. I left it the last time. I'd kind of tried to explain synchronous and asynchronous functions. It's not a term I like because I think it's misleading in some ways. It doesn't actually describe the nature of what we're talking about anyway, but that's the terminology. So I left it. I'd created a hardware interrupt that was driving. We still have a simple piece of code controlling the LED on D0, which counts and then resets or changes, flips a bit. Whereas I created a hardware interrupt to mess with the LED on D1. So that kind of is my introduction, and I'm going to use this mechanism. I wanted to use this mechanism to demonstrate a synchronous and asynchronous call to a function that we had, which was transmitting Morse. So I'm going to put those back into this code. So we want main to be exactly the same, but we want to change our implementation of Morse so that it's asynchronous instead of the current synchronous. So actually, given if I make two versions of the same code, we'll make a synchronous and an asynchronous version of the same function. And MPLabX may not be great at a lot of things, but it does manage configuration. So if we create a new configuration and we'll rename one of them to be sync and the other one to be async. Now, because I just renamed morse.c, I've probably lost it. Yeah, it's gone out of here. So remove that from project. And we'll now add the two files that we've just created, morse.asynchronous and morse.synchronous. And because we're in the current, this drop down lets us select a configuration. Because we're currently in the sync configuration, we're going to exclude the asynchronous from the current configuration, and if we move to the asynchronous project, we'll remove the synchronous. So if we go back to the synchronous version of the project, I better open those two. So if I get rid of the hardware interrupt out of this main.c, I'll enlarge this. If I get rid of the hardware interrupt, we're going to move that. That's going to become part of our asynchronous implementation. And the bit where we set up a timer, move both of those into our asynchronous function. And so at the last time I left it, I had the lights flashing, one controlled by the main loop and one controlled the interrupt. This code was our original code, which I'll flash back in. And sorry. So this is a synchronous function. So when we press the button and the LED is on, we're not going to return from our function call. The Morse TX, isn't going to return until it's finished. That's the last dot. So end of word, and now we're back. And that's synchronous. It has to complete. So we're going to change it to being an asynchronous. So we're going to edit the asynchronous project. And the main is exactly the same. So our application code isn't going to change. Our API is exactly the same. A dumb, badly designed API call. What's going to change is this code. So if I get rid of this from here and put it down towards the bottom, we want to run on an interrupt. Now the last time when I did the example with the LEDs, I was using interrupt 1, timer 1, which is a 16-bit timer. If you look at timer 2, 3, 4, 5, 6, 7, 8, 9, they're all independent 16-bit timers, or they can be combined into 32-bit timers. And that's what I'm going to do. I'm going to combine timer 2 and 3 into one 32-bit timer. And it's important to note that the actual ISR, the interrupt, is going to be generated on timer 3. But we're going to control timer 2. So that is going to make things a little, well, it's not a problem. It's just you create code like this. If we want to clear the interrupt flag, then we want to clear interrupt flag 3. But then if we want to turn the timer off, so it's t2 con bits dot t on is equal to 0. And if you look at that, we can get rid of those two. If you look at that ISR, you can see that it's a timer 3 interrupt. We're turning off the timer, or we're clearing the timer 3 interrupt flag, and then we control timer 2. So it could be, you could look at this and think, oh my god, there's an error there, but hopefully that will remind me in future if I come to this and look at it and think there's an error, that this is correct. So we want to get rid of this implementation of a loop which was doing all our time, and we were basically had the processor locked up doing nothing. And we'll get rid of all this dot dash functionality. It relied on that loop to do its transmission, so we're getting rid of all of that. And what we're going to do is we want to create a transmit buffer of, let's say, 20 things. And what things we're going to keep is going to create an enumerated type, called element, which is Morse elements. So we've got a dot, we've got a dash, we've got an inter element, we've got an inter character, we've got an inter word, and we'll keep a message end as well, just so that we know that we're at the end of a message and we can stop transmitting. So the type we're going to keep in their buffer, transmit buffer, becomes this 20 elements. So that's our data structure. We also need, and that's static. It's private to this file. We'll also keep a counter, which is our tx index, and that is the index into this buffer or array of the element that we want to transmit next. So once the interrupt is finished here, we've got the timer interrupt, we want to step through the transmit buffer. So we'll just basically call the function step. So we've got finished one transmission of one element, we want to step to the next. We want to do whatever the next step is in our transmission process. And Morse, this is the actual guts of it. This function, which is our API function, I usually keep anything begins with the name of the file as an API. It's public, whereas everything static doesn't. But this is our ugly synchronous function call that doesn't return until it's finished. So what normally happens in this kind of case when we're doing something like this is we're actually just gonna load up the transmit buffer. That's all we're going to do. So post increment the increment or the index. So first thing is a T, so we want a dash. And the second thing after that, that's the end of a character, so it's the intercharacter spacing, and that's a T, and that replaces those two lines. After that is our H, which is a dot. Well, it's 4 dots. It's a dot followed by the inter-element space, but we need 4. And the last one is going to be the intercharacter. So that's replacing loading up the buffer with a H, and this is going to be our E, which is a dot, and that's the end of word. And we can get rid of the remainder of this, which is our old implementation. So we load up the buffer. We better put I call it message end at the end of the buffer, so we know we're finished. And we better make sure that our transmit index of what we want to transmit is equal to 0. And now we want to call the step function as well. We've loaded up the buffer. We want to call the step function, which was also called from the end of the ISR up above. So when we load up the buffer, this API function will transmit the first element. Thereafter, we're going to rely on hardware interrupts. So we've got to do our step function. And make it static, so it's private to this. Sorry, I should have put that above to get everything in its proper place. So all we want to do now when we come to step through the buffer, we're going to need to switch on what we're looking at. So what we want to actually transmit is whatever is in the buffer at the TX index position. and that can only be what's been defined in our enumerator type. So we have a dot, we have a dash, enter element, enter word, and the end of the message. That's all that can be in the buffer. So for a dot, we simply want to turn on that LED. And break. But we also want to do the same for our dash, so we can just drop that into the same piece of code. The enter element, enter character, and enter word, they actually just want to turn off that bit. And then message end, we just want to return. Now I put a break there, it's a spurious break. Some compilers complain that it's there, some compilers complain that it's not. So each step, whatever's in the current position in the transmit buffer, we turn on or off the LED accordingly. After we've done that, we want to start a timer for that element. So tx buffer transmit index. And after we've that means we've finished transmission of that element, so we want to move to the next transmit, whatever's next in the transmit buffer. And now we need that start. We need the start function, which is being passed in a Morse element. I'm going to stick a prototype up above. Make sure everybody's happy. So now we want to start a timer, and it has to be on timer 2. So most things are going to be the same. We want to count the internal CPU clock. It's not a gated timer. We want to divide it by 256. One change is that we want a 32-bit timer. We want timer 3, or sorry, interrupt 3, timer interrupt, which is on IPC2, I think, to be at the highest, whatever that is. We want to clear the interrupt flag, which is flag 3. We want to enable the interrupt, which is interrupt 3. And now we want to set up our starting position and start counting from 0 in these timers. That's the 16-bit even timer number, that's the 16-bit odd timer number, and this is the 32-bit. So we need to set up both PRX and PRY, as well as X and Y of the TMR registers. So instead of simply doing TMR1, we want to set 2 and 3 to be 0. And now we need to set up what our target is, our destination, our target value on the timer, which is going to depend on what we're actually transmitting. So it's going to depend on, if I just copy this switch statement, it's going to depend on this. And if we switch this time on E, which has been passed into the function, now these things were grouped according to what they did with the LED. This time we want to group them in duration. So a dot is the same length of time as a dot is the same length of time as an inter element. A dash is the same length of time as an inter character. An inter word is on its own, and we shouldn't get a message end message, but just in case we'll stick a return in there. And all we want to do is set duration is equal to, I had 3 FFF. Let's change that and make the only piece of code which, or only good style of code I'm going to do is have a hash define for dot duration, which is 0x3FFF. So if it's a dot or an inter element, we want a dot duration. If it's a dash or an inter character, we want 3 times that. And if it's the inter word, we want 7 times that. And that's us. We only have to now load it up into duration, but we only have to load that up into PR2 and 3. PR2 is X is the even number, PR2 is the least significant word. So we want to cast this 32-bit value to a 16-bit value, and we want to AND it so we only get the lower half of that 32-bit value. Similarly with our the most significant word, we want to shuffle that down so that we get the top half is moved down into the bottom half, bitwise AND it with 16 bits of the lower half, and store that in PR3. So this is the least significant word, and PR3 is the most significant word. If I use the right terminology, MS. So set up our target value depending on what we're transmitting. Turn the timer on. Interrupts are on, flag is on. We actually want to turn timer 2 on. That would have been a bit of a doozy. And that hopefully will compile. And it didn't. Dot duration times 3 and times 7 is overflowing. 3FFF. 3FFF times 3. 3FFF times 7. I'm not sure why the compiler's moaning. Do you know, the simple way around this maybe is just I'll do 3 defines. Which is a bit stupid, but it'll just get us moving. So then BFFD and 1B FF9. Well, oh no, that. Stop. I'm not sure why that's now happy with those defines rather than actual calculations. I'll come back to that if I ever think about it. For the minute, let's go back. That's where we were with the synchronous version of the code, the synchronous version of the API. We start transmission, we lock everything else out of the processor and just loop, getting everything done. And then when we're finished, we pop back and things resume from where they were. That's the synchronous. So now I'm just going to we'll code in or program in our asynchronous version, which has similar functionality, just different, hopefully. So now, if this works, we got a dash, dot, 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 and a dot. Yeah, 4 dots. All right. Dash, 1, 2, 3, 4. Yeah. And as you can see, the two things are happening at the same time, so it gives the kind of illusion that we've got two things happening. They're not. It's all serial, but there's the illusion. And this is potentially not a good example of code. Morse code isn't exactly common, but that implementation detail of a difference between, we've got exactly the same function API signature is implemented in 2 different ways, and I'm not sure I agree with the use of the asynchronous in that context, but that's what we use. And you're either writing a synchronous function or an asynchronous function, and there is a time for both, and I'm sure in the fullness of time we'll come to an example where it makes much more sense to write an asynchronous implementation. But that's it for the minute. Next time, something else, hopefully. Thanks a million for watching.